All right, let's take a look at solving polynomial equations. So, first of all, when we're talking about solving an equation, what do we actually mean? So you've been seeing lots of solving equations. What we need to remember is that we're looking for determining essentially an x value that makes the equation true. So if you were to plug in that x value, the statement would work out. Okay. So how are we going to do that for the equations we're given? So oftentimes, and what's going to be helpful is setting your equation or getting it equal to 0. If you didn't have it equal to 0, rearrange it so that one of your sides is 0. Because then what we can do is we can solve the equation by factoring. So I'll just write that to the side. So make sure one side of equation is equal to 0, then factoring will work. To solve it. Essentially why it works is we're going to, in a sense, use this 0 the 0 theorem. I'm forgetting what it is. The 0 product property. That's what we're using. If two things multiply to 0 or more, then the individual parts can equal 0. That's what we're going to make use of. We'll see what we mean here. Okay, so we want to factor this. So we can either factor using factor theorem like we did previously, or use other methods like grouping. So don't forget things like grouping. In this case, the insides are 3 and -1, and the outsides are -3 and 1. So grouping will work. So 1 times -3. Okay, so let's use grouping. Let's common factor x squared, x plus 3, minus, and then x plus 3 is left. On the right, we'll still have the equal 0. This is an equation, so make sure you have your equal sign with the equation part, not in front, not like that. So make sure you don't have it in front. What we're doing here is we're stating that, in a sense, the left side is still equal to the right side. That's what we're stating for the equation. So now we have x squared minus 1 times the x plus 3. That's equal to 0. And I can further factor x squared plus 1 or minus 1. That's a difference of squares. So x plus 1, x minus 1, x plus 3. That is equal to 0. Okay, so the 0 product property says that if you have things multiplying to 0, well, the only way to get something multiplied to 0 is to have 0 as one of your factors. So we can just individually set each factor equal to 0. So x is equal to -1, or x is equal to 1, or x is equal to -3. So you have 3 answers. So there's your solution. X equal to -1, x equal to 1, x equal to 3 will make the left side of the equation equal to 0, which will make that statement true. So here I'll write the conclusion. Oh, and the last one should be -3, not 3. Okay, let's continue. 4x to the 4 minus 2x cubed minus 16x squared plus 8x. So again, we're going to do this by factoring. And to do this by factoring, we'll just check if you can first of all do grouping, and again, you can. So again, I just want us to remember those other techniques. Using the factor theorem is definitely one that we do need to know. But if we can do a shortcut like this, then definitely save yourself the time. So in this case, factoring will work with grouping. Not only that, you'll see we'll just do the grouping. You'll see also that we could common factor, but that will come in play when we do this factoring by grouping as well too. So We'll kind of do them both. So in the first set, we'll have 2x cubed that we'll pull out. And we'll be left with 2 and an x minus, well, 2x cubed is there, so just 1. 2x cubed divided by 2x cubed is 1. And then in the second set, I'll take out a negative so that we don't have that negative sign inside the first bracket. We'll take out an 8 and an x. And we'll be left with 2x and then minus 1 equal to 0. Okay, so that will leave us with 2x cubed minus 8x, 2x minus 1 equal to 0. Okay, and we always want to check, can we factor further? Well, if we take a look at this one, we can common factor 2x actually. And so let's take out a 2x, and what are we left with? We're going to be left with, well, x squared minus a 4, 2x minus 1. And well, that x squared minus 4, that's a difference of squares. So break it up into x plus 2, x minus 2, 2x minus 1. Okay, and then by the zero product property, since we have a multiplication statement equal to 0, well, one of those things multiplied will need to equal 0 for that to happen. So it could be any of them. So it could be x equal to 0, or x equal to negative 2, or x equal to 2, or 2x minus 1. Well, if you set that equal to 0, we'll solve to become 1 over 2. Okay, and there we have it. We have 4 solutions in this case. So yeah, all these kinds of questions where you're solving an equation, it really all comes back to, can we factor? Factoring is a key method to solving equations. Okay, 8x cubed plus 27. All right, that's a small little polynomial. And you might be thinking right away, well, it's not factoring by grouping, so I guess we need to go back to just factor theorem. And in fact, there is another way we can do this one. So to solve this one, we just need to remember this is actually one of our special cases we had way back at the start of this unit, a sum of cubes. 8x cubed is actually just is equal to 2x cubed. 27 itself is just 3 cubed. Or the cube roots would be 3 and 2x. So that means using our sum of cubes, the first part is just the cube roots, so 2x plus 3. The sign matches. And then it's just the square of those two numbers. So 2x squared is just 4 and then x squared. 3 squared is just 9. And then in the middle is the opposite sign. So since we had plus before, we have minus, and then 2x and 3 together is 6x. And there we have it. That is going to be equal to 0. So then we need to check, can we factor this? And you could try to find two numbers that multiply to, well, 9 times 4 is 36. So two numbers that multiply to 36 and add to negative 6. Spend some time doing that. You may get stuck. So the other thing we can check is, well, thinking back to what you've seen in the past, but maybe not thought too much of, is the thing inside your square root of the quadratic formula, the discriminant. You can use that to count the number of zeros of a particular quadratic. So we can see, does this actually have a 0, this part? So b squared minus 4ac, that was the discriminant, which would just be negative 6 squared minus 4 times 9. And we'll guess what? That's going to be 36 minus some sort of 4 times 4 is 16 times 9. It's going to be a large number. Basically, ends up being less than 0. That's really the thing that matters. So no zeros. Or no solution to that quadratic formula. Okay. No. So therefore, 2x plus 3, that's the only part that's going to possibly be equal to 0. So that's going to be the only solution. So therefore, x is equal to negative 3 over 2. All right, so yeah, there are situations where not everything can factor. But having said that, it's not really what we like to do as mathematicians. So if we look at x squared plus 1, are there any solutions to that? Well, we could actually just rearrange this one. You don't even need to do any sort of quadratic formula. Since there's only a single x, you can isolate for it. And if you try to do that, you will get the square root of negative 1. And as we know, you can't take the square root of a negative. Because if you take the square root of a negative, well, two numbers multiplied, or basically a number multiplied by itself, will always become positive. And so there's no solution. So no solution. At least as of right now, with the numbers that we work with. And mathematicians, we like to have solutions, even in situations like this. So what has happened in the past, mathematicians have worked with this kind of thing for now hundreds of years, is we've created a new number set called the complex numbers. So just in the situation like above, when we encounter these negatives inside square roots, it'd be nice if we could actually continue to work with those numbers. And so what mathematicians have done is they have created this thing called the imaginary number. Imaginary maybe isn't the best word for it because it is a number and it gets used. We label it with the letter I, and it is equivalent to the square root of negative 1. And now whenever we encounter a negative square root, we can always rewrite it in terms of I and get an actual solution. So yes, does it feel weird? For sure. And I'll attach a few videos in our course, I guess outline, the unit outline, if you want to look a little bit more in depth into these things called the complex numbers. We won't really go too in depth. We're just going to really get at the idea that they exist, they're there, and we can make use of them to solve these kinds of equations. But yeah, essentially it's just one level up. So throughout, let's say, math history and human history, we've been building up numbers, the number sets more and more. Humans started with just the natural numbers, just counting numbers. There wasn't a need for fractions. There even wasn't a need for negatives. And it took time eventually for humans to figure out, oh, maybe the number 0 would be useful. Maybe having negative numbers would be useful. They got added into our number systems. Fractions, eventually, we figured out, okay, these are things we can work with and actually write down. Same thing with even things like square roots and rational numbers and irrational numbers once you get square roots that don't have nice decimal values. So something that's been steadily being built up, these numbers that we work with, and this is kind of just the next step up. But it definitely has an odd feel to it. Okay, let's try to solve something using the complex number I. So we're going to look at just x squared plus 2x plus 2. So if you try to factor that, it's not going to work. So you move on to the quadratic formula. The quadratic formula being negative b, so negative 2 plus or minus b squared, which is 2 squared, minus 4ac, which is 1, 2, all over 2, that's a crooked fraction, all over 2 times a, which is 2 times 1. So that's the quadratic formula. Now let's just solve it out. And what you're going to see inside the quadratic formula, the square root, you're going to have 4 minus 8, which is negative 4. And in the denominator, you're going to have 2. Okay, so negative 4 is not negative 1, which we just said was I. But we can rewrite negative 4 in terms of I. And how we can do that is we'll basically just split it up. Square roots, you can always split up as two numbers multiplied together, and any negative number is just -1 times whatever you're looking at. So -4 is the same as 4 times -1. And then that's how we can write it in terms of I. So what I'm going to do is I'm going to write this as -2 plus or minus, well, square root of 4, we can take that square root 2, and -1 is going to be I. So -1 becomes I. Root -1, I should say. And that's all over 2. What's going to happen in this case? We have the numerator. Both the numbers are actually in terms of 2, and we're dividing by 2. We could just actually divide by 2. So divide that 2 into both parts, and you get -1 plus or minus I, or therefore x is equal to, I'll write out the two separate answers, -1 plus I, or x equals to -1 minus I. And there we go. That is our solution to that quadratic, now using the complex numbers. So yeah, this is really the only part we're going to get into complex numbers. We're not going to really go into them too in depth. It's just when you use the quadratic formula, you see that square root with a negative in it, you can now replace it with an I. Okay, and let's do a little bit of extra work with solving. I mean, in this case, it doesn't look like we're solving. It's just asking us to sketch this function. But essentially, we're going to use the skill of factoring, like we were doing with the solving questions before, to be able to sketch this. So we did sketching in the previous unit, and what we did with sketching in the previous unit is we used things like the end behavior, the intercepts, to sketch out the graph. And the key thing is we always had it in factored form. So really the only thing is, all we're going to do is factor this first, and then sketch like last unit. Okay, so what are we going to check to factor this? Well, we can't factor by grouping, so we're going to use factor theorem. So we have -6 on the end there and a 2 in front. So we're going to check factors of plus or minus 1. For the 6, it's 1, 2, 3, 6. And for the 2, 1 or 2. So I'm going to just start with the whole numbers, 1, 2, 3, 6, positive or negative, and then we'll see what we get. So if you do f of 1, 2 plus 3 minus 11 minus 6 is not equal to 0. Okay, let's do 2. 2 times 2 to 3 plus 3 times 2 squared. Let's write that out a little more carefully. Minus 11 times 2 minus 6. Okay, that's going to be 16 plus 4 times 3 is 12 minus 22 minus 6. Well, you get 28 minus 28 is actually 0. So therefore, x minus 2 is a factor. Okay, so let's factor that using that. So I'm going to use synthetic division. Let's write out the coefficients. 2, 3, -11, -6. And on the outside, we have the number 2 itself. Okay, so drop down the starting number, the 2. 2 times 2 gives us 4. Combine those two numbers, 3 and 4. Add them together. That gives us 7. 2 times 7 is 14. And then the next column, 14 and -11, gives you positive 3. 2 times 3 is 6, and that's good because 6 and -6 cancel. Give you remainder 0, which is what we just had up above. All right, so then that means f of x is equal to x minus 2, 2x squared, plus 7x, plus 3. And then we just need to factor 2x squared plus 7x plus 3. It's complex trinomial, so we need to figure out what multiplies to 6 and adds to 7. And that's just going to be, it looks like 6 and 1. And then I'm going to decompose that middle term into 6 and 1. So 6x plus 1. And it doesn't matter what order. So if I did x plus 6x, you'd still get the same answer in the end. So you will end up factoring this as common factor now, because when you do this, you're essentially setting up a grouping situation. So 2x plus 1 is what I'm left with, and pull out a 3, and you're left with 2x plus 1. And then that will lead us to x minus 2, x plus 3, 2x plus 1. Okay, we've got it in factored form. So now we can approach this exactly like we did last unit. So we can get our end behavior. We could do that either from the standard form, actually, or this factor form. So either way is fine. So what we have is odd degree. It was cubic, and it's a positive lead coefficient. So that means it's like a regular cubic going from the bottom left to the top right, which is quadrant 3 to quadrant 1. Okay. And then the other thing was the intercepts. So we have the x-intercepts. And that's why we need to factor, because now we can just easily get our x-intercepts, because the x-intercepts are just when is the function equal to 0. That's actually what we're doing in our solving problem or solving equation problems up above. So in this case, it's just going to be 2, negative 3, and negative 1/2. And they're all order 1. So remember, we need to include the order. That tells us the shape of the graph around those intercepts. So in this case, nothing really fancy is happening. And the y-intercept, you can find that either with your factored form or going back to your standard form. The y-intercept, when you plug in 0, is always just that constant term. So it's just negative 6. Okay, let's plot this. So we'll try to keep things to scale. So negative 6 down here. I will do 2, pretty close. Negative 3 will be like half the distance of what 6 was. So I'm going to try to keep this all to scale, both vertically and horizontally, since all the numbers are fairly small. Negative 1/2 will be pretty close to the y-intercept, or the y-axis, I should say. All right, and let's label these. So negative 3, negative 1/2, negative 6, and 2. Okay, and I'll draw this in red. So we're starting in the bottom left, going upwards, going straight through, going through negative 1/2, going through negative 6, and going back up to 2 and upwards. And there we go. That is our graph of f of x. And that's factoring and using it to solve equations, including factoring to sketch a graph.